Hello, everyone. So to get a little bit onto the agenda, today's session will be about, well, network appliances and some new challenges that we face with the new technology. And at the core of our talk will be 5 vulnerabilities that we disclosed to F5, and quite a bit of introductory material to why they are important, because those vulnerabilities are kind of a recurring thing in network devices, especially in the recent years. So my name is Vladislav Babkin, or Vlad Babkin for short. I'm a network and web hacker for the most part, also a web developer. I have around 10 years of experience in security specifically. I'm also a very long time CTF player, so I have been playing since like 2015 maybe, or even earlier. And right now I'm working as a security researcher at Eclipsium. So yeah, that's enough about me. But before we start to dive into the newer network devices challenges, let's discuss a little bit at how they actually evolved, because this is very relevant to the talk. And in my opinion, really, really important topic. So at first, if you look at attack surface, the devices were pretty simple. Like sometimes they might have been a simple binary, like a single binary firmware, something like this. And there were not a lot of attacks on them, like at the very least not publicly known. And most of the things listed here are different nation-state groups performing those attacks, or leaks from nation-state group tools. And attacks were pretty pricey. So some very popular things like VPN filter was a very well-known attack, or shadow brokers drama was pretty much a big thing, right? But then in 2019, one very big event happened, like really big and important event that pretty much just changed the entire field here. It was SolarWinds attack. While it was not directly related to network devices, it was a very big and popular case of an infrastructure attack. We just got everybody, because everybody is using SolarWinds. And after that, this is what we see. So we just see a flurry of new zero-days vulnerabilities in all of network devices imaginable. We see a lot of people abusing them. And in this case, it was not even nation-state actors, but just random script kiddies sometimes. Because some of the attacks, some of the vulnerabilities are tweet-sized thing. Like it's a tweet-sized exploit that's really easy to reproduce once you know what the vulnerability is. And what we observed is that sometimes it took maybe a day to actually weaponize for even a very small attacker, like small-time people who just try to install minor malware on them. And notably, if you look at 2020, 2021, 2022, we have 3 different F5 zero days. We see Citrix as a recurring topic. We see Fortinet as a recurring topic. So pretty much, we are getting the same vulnerabilities. And at some point, it got so bad that CISA actually started to issue a directive to fix all of that, and that we need more secure software, right? So that's pretty much short history, short intro. And to give some extra context, as I said, some attacks are literally tweet-sized. So in this case, I just took a screenshot of 2022 1388, right? And that's the full exploit. So it literally fits in a single screenshot. And the exploit is also pretty simple. We just instruct the device to run a command, right? So we are facing really basic web application problems. And by the way, it's not plaguing just the network devices. It's plaguing things like BMC, like baseboard management controllers, which that manage your servers. They also got more powerful, and as such, they also got basic web apps running in them. So in fact, modern devices are ultimately an x64 platform, which basically all your computers, PCs use, and they face the same issues as them. You have a web application running on them, and because they have so much firepower now, you can see PHP, Lua, Python, all of the scripting languages on them, not just compiled binaries. You also have central manager appliances, like a central manager panel that manages all of them at once. And it has even databases, so you can face database-related issues. And now we have a full-scale Linux, but it only has usually a single user, like for example root. And everything running is running as that user. So we are back to the 90s and the good old times when you just had to get a code execution and suddenly you got your entire machine. But we are facing this right now on network devices. And while before they were pretty small and they didn't have a lot of space, so you had to narrow down what's installed on them, Nowadays, it's not the case anymore. They come with all of the tools imaginable, so attackers sometimes comes into the platform and already has tools to interact with web, like curl, wget, and everything else. And they don't even get OS updates normally because of different complications. I'll discuss a little bit more on this shortly. But they normally don't have something like an attended upgrades package or anything like that. So they slowly get outdated without ever fixing themselves. And just to add to the point, like here are two motherboards from two devices. On the left, we have Cisco ASA firewall. And on the right, we have a 5 big IP disassembly. And if you, for a second, just close with your hands logos on them, it will be really hard to tell that these are not a normal server with some very specific hardware for some specific task. So we have a CPU right here. We have memory sticks. For example, here, we have a hard drive. We have all of the normal server stuff with maybe, oh, hey, whatever this is, right? So, but if you literally close the vendor, it will be really hard to identify them as something other than a server. So, and that's a very interesting point. It's just normal server hardware. And if you look at the shells of those devices, it's also just normal Linux shells. On the left, we have Big IP Next Central Manager shell. And if you look at its file system, we see normal Linux folders you expect to see, like boot, dev, etc. With maybe like a couple of files that are specific to the platform, like version. But on the right, we have a much more limited device, a baseboard management controller shell. Specifically, it's a MegaRack shell. And you can see that it uses some interesting username called sysadmin. But if you actually dig through its files, you will find out that sysadmin is user with U80. So it's pretty much root, but renamed for some reason. And you also see some folders that are not normally seen on Linux hardware, like backup config. I don't know how to read this, so that I highlight that there are only 4 letters. Maybe some configurations for Redis, etc., etc. But you can still see all of the normal Linux folders. Interestingly enough, the hardware on the right actually is using squashFS. So problems with updates there is much more hard to solve than on many other platforms. You cannot just install new stuff to squashFS. It's meant to be read-only. So actually solving all of the issues that I named is not so simple. You cannot keep them updated automatically because they sometimes have very limited space and have to deal with all of this, right? But bottom line is, we have Linux boxes from the 90s, but we're in 2024 with 2024 tools. And we know a lot more about attacks on Linux now. And we can just apply all of this knowledge that previously was not available to break those boxes. But the worst part is yet to come. It does not really end there, because normally what you get on these new boxes, the network devices, is usually a single glass pane view of the device. You normally don't even get a shell. So for example, the shell that I did show you on MegaRack device, this one on the right, it's not normally even available to the administrator. So we had to exploit a vulnerability in the device to get to this shell. So if attacker actually managed to set up home here, I would not see it. Like as a defender, I would literally not see it until I exploit the device. Or maybe unsolder the chip and pretty much dump the firmware, which is, as you can guess, is not very productive on a large deployment, right? So, and the question is, the big question is, how do we, in this case, we as an industry, actually fix all of those problems? Because we cannot just dump this on a vendor. Vendor cannot define good standards normally. And in this case, there is a good question on how do we even approach this. And to this point, like I collected 3 links at the very least. I'll probably click through them and talk a little bit about it. So the first link is from CISA, and CISA is pretty much calling for urgent need for memory safety in software products. So CISA is asking all of the new developments to be done using memory-safe languages, like say Go, say Rust, maybe scripting languages which are protected from memory leaks and whatnot. This will protect us from a lot of binary exploits that happened in the past, like buffer overflows, etc., right? Then DARPA is pretty much, I decided to click on the slide and not on the link. So DARPA is asking us to pretty much eliminate memory safety vulnerability once and for all. I would say this headliner is pretty much speaks for itself. No extra comments needed. And then also CISA was talented to do like secure by design systems where we should eliminate command injection vulnerabilities. And the common topic here is that all of those are targeting one specific vulnerability at a time. It works, and I will just in a moment show you how this approach can be applied in production and was applied by at least one company. But it doesn't really protect you from everything. We have a lot more vulnerabilities than just memory safety related bugs, command injection bugs. We have a lot more than that. So a little bit of a side story is Big IP platform in general. F5 Big IP is pretty much an application delivery platform. So it handles all of the things like TLS registration, like WAF, deployments of the application. It has a lot of tools to actually manage your application. And the platform got hit with things like 2022-1388 that I just showed you on a screenshot. So really simple exploits with just command injection. Or something more complex, but still something that fits in one tweet. And I don't know why they decided to switch to a Big IP Next platform and why they decided to do the rewrite. But judging from what we saw on the inside once we opened the platform up a little bit, they definitely had security in mind as well. So they pretty much created a central manager appliance, which manages all of those F5 Big IP Next devices at once. And it's a complete rewrite of the platform. So there is no more single user thing going in there. And what they used were Kubernetes and Golang. In this case, they created a platform based on microservices. And on the right, we have a screenshot specifically from Central Manager. But if I show you the same screenshot from the device, it will still have similar microservices. So they literally went all in on the Kubernetes, Docker containers, isolation, and memory safety. So we have over 30 microservices in both the device and Central Manager. And if you look through here, you might notice that we have a Postgre database. So it's not a single account in the Postgre database. They have an account per microservice with really good access controls. So you cannot access tables from another microservice using credentials from your current one. So this is supposed to limit the scope for things like SQL injection or credential leaks. And to add to that on top, they actually used HashiCorp Vault for credential management. So they literally went all out to actually make it more secure. And again, this closely follows the CISA goal that I just showed you for memory safety. So it does indeed use memory safe languages. It even uses containers like distroless containers, and it even has separate users in those containers, so that stuff is not even running as root in there. So it does, in fact, improve security posture of the device, so no questions there. But let's dig into the device first. So in this case, I will be discussing virtual devices here, but physical device is no different. So they still have all of the same things, just slightly harder to get to. And notably, steps for virtual device and for central manager in this case are similar. And after the device setup, you as a researcher or as a defender, you can get into an admin shell, at least in the virtual device. In the physical device, it will be slightly harder, but not that much more difficult. And here is pretty much a screenshot of the shells. And you get in as an admin user, and admin user has sudo privileges. So you get pretty much root access. OK, what next? So in this case, we do have to take a page out of DevOps books and how they manage Kubernetes containers. So kubectl get pods is how you would list everything that's running on the device. And then using the command, I'll probably not read it out, you can actually run, for example, SH binaries inside of the containers. One notable point is that it will not work with Go containers because they're using distroless containers. They literally have a single binary with minimal files for it. And software in there is not even running as root. So I just went through maybe not all containers, but quite a few of them and checked its privileges. But those containers are still not magic. And you can still find a lot of interesting stuff on the device. Like if you browse it long and hard enough, you may stumble upon this beast of a path, which just very long. But once you get there and you list what's in there, you see all of the container's contents. like their file systems for each container. And in this case, like I just tried to find all of the Go binaries. And for example, here we have a DNS feature binary. So as a researcher, you got access from the root shell to all of them, and you can actually research the device pretty easily this way. Once you actually have the files, you can reverse engineer them, read the configs. So you basically have enough firepower to actually do something. Okay. Let's be honest here. This outright destroys a lot of attack vectors. So even if you get command injection, how are you going to exploit it? Like your command injection might be just in a Go container with the single Go binary that's already running. Good luck exploiting it, I guess. So you have to bring tools to those containers, and it's sometimes much harder. Go is memory safe, so there is probably not going to be an easy binary attack like before. You're probably not going to get a buffer overflow, heap overflow, or anything of the sorts. You probably are not going to get instant root either, so even if you manage to bypass all of the hurdles here, you are running in a container. So good luck breaking out to the host shell. And also, because it's using microservices, it has less poorly designed features just by virtue of using microservices. You cannot design something as poorly when you have all of those walls in between things. So even without further analysis, it's obvious that they had to put a lot more time into the design there. So you're probably going to hit isolation issues for when you try to exploit the device. But does this solve all of the issues? And our claim is that no, it doesn't, and we can demonstrate that. But also, it doesn't solve them even when you apply just pure logics, all right? So first of all, we are now using microservices. And as we have microservices and inter-device interactions, like we have one appliance calling another, server-side request forgery issues are probably going to be present if you look hard enough for them. Because there is a lot of HTTP and maybe other communications going on in between all of the microservices. That's how they operate. So that's a new surface which never existed before, network devices which might be exploitable. We are not sure yet, but just pure logic tells us that it might be there. Other injections, other than command injection, might still exist and be useful. So while we do have separate database accounts, there is nothing inherent in Golang or Kubernetes or any of the technologies named that prevents SQL injection from appearing, even if you have access only to a small portion of the database. Things like XSS, insecure direct object reference issues, validation-related bugs, and whatever other bugs you can imagine, they don't really get a lot of coverage from Kubernetes or Golang either. So you probably cannot type juggle, but that's it. There is no further coverage. And there is still no solution to component freshness. So the device arrives as is, and until you update it, it just stays the same. And this list is probably not even exhaustive. So let's see some of the vulnerabilities in practice. And I'll just demo what we found. So I'll try to make the demo go live. So if it breaks, I will switch to a recording. So, and the very first issue that we found is pretty much the aforementioned SQL injection in the login form. So they made all of the fixes, all of the changes, all of the important work to actually make it memory safe and prevent command injections. But because there was no standard to follow, no standard to actually check for, say, OWASP top 10 bugs, they managed to miss an SQL injection. And the attack is here, and it's in login form. And we use it specifically to, let me actually run this exact attack. So we use it to leak the admin password hash. So it's leaking the hash 1 byte at a time. And I'm running over VPN connection, so it will take a moment to actually start showing the first character of it. But let's give it a bit of time, and I will keep talking about it. So while it's an injection in the login form, theoretically, it might be possible to completely bypass authentication. But this attack proved to be much more complicated due to specifics of how it is implemented. So we never actually finished it due to time constraints. But the attack might be possible to completely bypass authentication, just much harder to achieve than something like a hash leak. And as you can see, hash started appearing. And this is, just from the header of the hash, is a bcrypt hash with a cost of 6. To put it into context, modern recommendation for password hashing, if you use bcrypt, is to use at least 11 as the hash cost. And cost is exponential, so it's not 2 times as low, it's exponentially lower. And that's very important because once we actually started to try to brute force it, just to see how fast the brute force would go, a single 4090 card can go at 110,000 attempts per second. A well-funded attacker can have millions per second easily using either more GPUs than we did or using FPGA arrays. You can pretty much Google the article on people who did it. And in the meantime, hash managed to leak 5 characters. So as you can see, the hash leak is very practical. And this is what you would see if you let it run until the end. I will probably abort this one. So once you actually brute force this hash, you obviously get as much as an admin would in the system. And let me actually show you the console for the device and how that would look like. So I obviously have credentials for it. So when you actually log into the console, you get pretty much admin account. So you don't get full bash shell or anything of the sorts, but you can still manage users, manage of the big IP Next instances. So our injection was actually in the central manager appliance, right? So we get access to pretty much the same things that your system administrator would, right? So we can see the device versions, we can reconfigure anything we like. But that's not where vulnerabilities end. There is at least one other issue which is much more interesting to discuss. So once you actually break into the device and you have admin password somehow, or you did bypass authentication, as I mentioned, how do you persist? Like, admin can just change his password or something that you can no longer brute force, or maybe just patch out the vulnerability because F5 released patches for this now. Well, you can create users on specific devices. So you can pretty much connect to specific big IP devices and make users on them using Central Manager. This is pretty much the SSRF issue, again, I just talked about. When you attach big IP Next device to the Central Manager console, it removes all of the users on that device. And users no longer even show up in the UI. But using an SSRF issue where they don't control the URLs that you can call on the device, you can make new users. You can just forward a make user request through the Central Manager and just make a user that's no longer visible by the admin. And I just pretty much did just that. And this is my new user on the device. I can pretty much copy this here. Then I can paste it here, right? Just so that we are using the account we just created. And I can then go ahead and log in on the implanted devices, right? And with this, I can do anything on the device that I would like. So I got full management of the device. I'm using it to just show a bunch of device data, like, for example, basic device information, like sys management IP addresses or what platform it's running on, list all of the available device logs, and just get a couple of lines from a log file. But I can reconfigure the device as I can see fit. This user has full admin privileges on the specific big IP Next device that's being managed, which is pretty bad. So even if you as admin patched your system, changed your password, checked that there is no remaining attacker presence in the Central Manager console, attacker can still have this user, which is nowhere visible in the Central Manager console, and the only way to detect them is by actually abusing the same exploit. So I have created pretty much a use of this exploit which instead of making users, is getting the users using, again, the same SSRF vulnerability. And here is a list of what I managed to demo so far, right? So I need to test the exploits, and obviously I created a whole bunch of them. So yeah, and ours is, I believe, this one. So we can actually detect those users, but you have to use the exploit to do this, which is pretty much was at the start of the presentation. As a defender, you still don't get the correct view. So the only way to detect those users is like this. Or you can unscrew the device and dump the hard drive or reactivate the shell, whatever you prefer. So neither of the two options are great because you have to decommission the device to do this, right? So we have a total of 5 vulnerabilities, and I showcased 4. There are actually 2 injections, which lead to similar results. One is an SQL injection, and the other is an OData injection in the same form in a different field. So we get 2 for 1. SSRF issue that I showcased does not even have a CV number, and I will comment on this, why closer to the end of the presentation, and the weak bcrypt hash. What I didn't showcase, but it still exists, is that once you actually log in as an admin, you can reset your own password without current password. So if you logged in somehow, or you managed to just come to the admin machine, you can pretty much reset his password without his previous one, which is not so great. Again, WebApps 101 tells that this is not normal. So, but you still can do this, I just didn't demo it. So, as per why we didn't get CV numbers, F5 pretty much told us that those are not vulnerabilities because they require your admin privileges to use. And there is nothing we can do about that, unfortunately. But we did notify the vendor. So, and conclusions for the exploit is that every listed vulnerability, every single one, is an OWASP top 10 issue. So we have 2 injection vulnerabilities, 1 cryptography fail with too low hash cost, we have a broken access control, and we have an SSRF issue, right? All of them can be classified easily as something very common to the web applications, and even after applying whatever was in the articles to the nines, they still exist. Additionally, all of the microservices do depend on some libraries, for example, but it's really hard to tell because a Go binary is a Go binary. It's pretty much just a single compiled binary. You need to pretty much decompile it somehow or disassemble it to get all of those libraries. So bill of materials would be great to have, but we don't have it. So supply chain playbook should apply here. And if we had something like bill of materials, it would be much easier to check what's on the device other than just trying to reverse engineer and browse it. But oh well, we cannot have everything. And modern devices are actually very, very complex beasts. So while before we probably had like 1 binary running on the device, now we have all of this beast of a microservice interaction and a lot of different issues related to that. So we have previous lancing surface arising. So, and the key takeaway here is that many of the past vulnerabilities and even vulnerabilities in this device could have been prevented with just better approach to software engineering. Like vendors normally don't apply it to firmware level attacks due to lack of pretty much standards. So there is no compliance that says that the network device that you supply to, say, federal government must be protected from OWASP top 10 bugs, right? So there is just no such standard, at least to my knowledge. And vendors are free to say that OWASP top 10 bugs are not an issue if they require admin authentication to abuse. So there is no standard to speak of which we can point to them. And haphazard process improvements, they do help. I pretty much just showed you one such process improvement. But because the vendor had to create this process from scratch, they couldn't cover everything. So it's not a single vendor problem per se. And we just seen an example of Big AP Next that it covered a lot of things, but not quite everything that it should have covered. And again, as I said, vendor response. So to leverage SSRF issues, you need to have admin access, and they cannot be directly leveraged to impact the security of the product, and we will not even patch it. So SSRF vulnerability is not patched in the latest release. And again, due to lack of standards, due to lack of compliance standards, we cannot just point the vendor to say this compliance thing and say, okay, you shouldn't have an OWASP top 10 issue in your product. So, and overall conclusions are as follows. So isolation and memory safety are really good, really important. They don't fix everything. So even a really good example of this applied, and I do think that what I just showed you with Kubernetes is really a good example of isolation and memory safety. It shows that very basic vulnerabilities still exist. So you cannot fix SQL injection with memory safety. It's just not how it works. And to be honest, we also need a lot more tools and approaches from software supply chain applied to firmware. And by this, I mean, for example, SAST tools in the pipeline, which could pretty much warn you about SQL injections, or bill of materials for all of your devices, where you can just see what's on the device and find vulnerable libraries which might be vulnerable in a year, or like just right now might be outdated. Or, for example, you can have a much better, much more advanced software development lifecycle, which we already have by now with all of the tools present. So there are multiple tools which can be used here, not just basic pen tests. Maybe, again, pen test requirements for the device to be pen tested like once a year or something like this. And last point is that F5 did actually improve the security. So getting a full host-level code execution is going to be harder. Like, as I have just said, we got access to the admin console. We got access to the specific device. We managed to persist our access. But we never got something like a full bash shell on the device or anything of the sort. So they did, in fact, improve security. Just, in my opinion, not really enough. So, and I don't even know that if it is their fault to the large extent. So with this, I think my presentation is done. And I have a little bit of time left for questions as I see it. Thank you for your attention.